Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind, and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into one of the strangest, most beautiful ideas in all of physics and philosophy, that the universe, as we imagine it, might not be an independent thing at all, but a kind of shimmering interface built from information, perception, and participation. A story we're not just reading, but helping to write. But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe, only if you truly find these calm explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from, and what time it is for you right now. It's always such a joy to see all the places we gather from, each of us in our own little slice of time. Now feel free to dim the lights, maybe turn on a fan for a soft background hum, and let the world around you fade to a quiet hush. Take a slow breath, let your shoulders loosen, and your eyes grow a little heavier. And if your mind begins to wander, that's perfectly fine. Let it drift. We'll still be here, gently unfolding the story. Tonight, as we drift into this calm exploration, we'll begin not with stars or equations, but with something closer, something deeply human, the way your mind paints the universe it believes it sees. You open your eyes in the morning and the world rushes in. Light, colour, sound, the soft clinking of cups in the kitchen, the faint hum of traffic beyond your window. It feels immediate and solid, as though reality itself were pressing gently against your senses. But what you experience is not the world itself. It's a translation, a quiet, continuous dream your brain builds out of electrical whispers. The philosopher Donald Hoffman likes to say that perception is not a window onto the world, but a user interface, like the icons on your computer screen. The little blue folder you click on isn't really made of blue light or cardboard edges. It's a convenient symbol that hides the swirling chaos of circuits and code beneath. Evolution, Hoffman argues, didn't design us to see the truth. It designed us to survive. Accuracy is expensive. Usefulness is enough. If you were to see the world as it truly is, raw energy fields, particle interactions, light waves stretched and compressed by motion, you wouldn't make it out of bed. Instead, the brain paints over the infinite detail with broad, practical strokes. It shows you a table, not a lattice of atoms vibrating in emptiness. It shows you a colour called green, not electromagnetic waves of roughly 500 nanometers. It shows you something you can use. Colours are the mind's poetry, not properties that exist out there, but interpretations. Honey tastes sweet because sweetness meant safety, energy, survival. The scent of smoke smells sharp and urgent because somewhere deep in time, that signal meant danger. Every sense you have is a tiny shortcut written by evolution's long and patient hand. Even the way you see space itself, the room around you, the corners, the depth, is a story the brain invents. Light doesn't carry depth. It arrives as flat patterns of brightness on your retinas. Depth is your brain's best guess, assembled through experience and motion. When you turn your head slightly and see how shadows shift, your mind triangulates the difference and produces the illusion of a solid world. You live in that illusion every second, and it works so well that you forget it's there. It's tempting to think of this as a flaw, but it's actually a masterpiece. The world you perceive isn't false, it's functional. It's the version of reality that lets you move, eat, speak, love. The physics behind it may be terrifyingly complex, but the interface keeps things gentle. You don't need to understand quantum electrodynamics to catch a ball. You just need your brain's evolved shortcut. The more scientists study the brain, the clearer it becomes that it is a prediction machine, not a camera. It doesn't passively record the world. It constantly guesses what's out there and then checks those guesses against incoming data. It fills in gaps before you even notice them missing. That's why you can read a sentence even if some letters are smudged, or why you think you saw a face in the dark before realizing it was just a coat hanging on a chair. The mind is forever completing the picture, turning the unknown into something comfortably known. In a sense, perception is an act of kindness, your brain trying to keep you from drowning in the raw data of the cosmos. Out there, light has no colour, sound has no pitch. Time itself may not even flow in the way we think it does. All of that is layered on afterward, like filters added to an image so that it makes emotional sense. If you've ever looked at an optical illusion, two lines of equal length that appear different, or a static image that seems to move, you've glimpsed the gentle arrogance of your own perception. The brain insists on interpreting, even when reality refuses to cooperate. What we call seeing is really a quiet negotiation between the outside world and the inside one. Hoffman's mathematical models go a step further. They suggest that statistically, creatures that see reality as it truly is don't survive as well as those who see a simplified version. The organisms that endure are those that see what they need, not what is. If your vision of a ripe fruit tree tells you where energy lies, you win. If it tells you the molecular truth of chlorophyll, you starve. And so our eyes, ears, and minds learn to compress, to ignore the unimportant, exaggerate the useful, and smooth over the strange. Like a painter choosing only a few colours to suggest the entire horizon, evolution learned that a little distortion is a small price for survival. The universe, as far as we can tell, doesn't shimmer in colour or hum in melody. Those are interpretations, beautiful ones, but human ones. If a camera were to capture your morning scene, it wouldn't taste the coffee's warmth or feel the soft pull of memory that coffee brings. Those are constructs of a brain steeped in history and meaning. And yet, what a marvellous illusion it is. An illusion that feels, loves, remembers, wonders. One that can gaze up at night sky and imagine itself small, or infinite, or both. The interface is not the truth, but perhaps the truth in its own way needs the interface to be seen at all. If the world we experience is an image rendered in the mind, it raises a gentle question. What is the projector? Where does the light of experience come from? And if perception is an interface, what lies beneath its surface? As we drift further into the story, we'll begin to follow that question, to the realm where observation itself doesn't just reveal the universe, but seems to help create it. Imagine standing in front of a mirror, watching your own reflection move as you raise a hand or tilt your head. The image seems faithful, yet you know it isn't you. It's a translation, reversed left to right, flattened into light. In much the same way, your perception of the world is not the world itself, but a living reflection the mind has crafted for you. Neuroscience tells us that between the light entering your eyes and the image you think you see, there lies a storm of transformations. Photons strike cells at the back of your eyes. Those cells don't see colour or shape. They send electrical pulses, tiny codes, to the visual cortex. From there, patterns are woven and interpreted, compared to memories, adjusted for context. By the time you think you're simply looking, you've already built an entire scene inside your head. But this translation doesn't aim for precision. The brain's highest priority is not to recreate the world faithfully, but to create a version of it that's fast and useful. Like a good artist sketching in lines rather than tracing every detail, the mind prefers pattern over perfection. It wants the forest, not the leaves, the meaning, not the mathematics. This is why we see illusions, not as errors, but as evidence of creativity. Consider the checkerboard shadow illusion, where a square in shadow appears lighter than an identical one in the sun. The mind insists it must be lighter because it knows how shadows behave. Or the moon illusion, where the moon at the horizon looks much larger than when high in the sky, even though it isn't. Our brains quietly stretch and scale space itself to fit the story they expect to see. Each of these illusions is the mind doing exactly what evolution designed it to do: filling in, simplifying, predicting. Perception isn't a camera, it's a storyteller. It takes limited data and invents a coherent plot, because coherence, not accuracy, is what keeps us alive. Information theory gives us a language for this. Every act of seeing, hearing, or touching is a form of data compression. There's simply too much reality out there to process it all. Instead, the brain filters the torrent into something manageable, a stream of symbols that capture what matters most, patterns that predict what comes next. Scientists sometimes describe the brain as a prediction engine, forever minimizing surprise. It doesn't wait for the world to act. It guesses first, then updates those guesses when reality disagrees. You can feel this prediction in action in everyday life. When you reach for a doorknob, your brain has already anticipated the coolness of the metal, the weight of the pull. When something different happens, when the door sticks or the knob is warm, you feel a tiny pulse of surprise. That pulse is your brain updating its internal model, rewriting its story to fit new evidence. Reality for you is not a stream flowing into your senses, it's a dialogue, constantly negotiated between what is and what you expect. And that negotiation extends to almost everything you experience. The reason music feels emotional is that it plays with prediction. The mind anticipates where a melody will go, and when it's led astray or rewarded, it responds with pleasure or suspense. Even conversation follows the same rule. When someone pauses unexpectedly, you feel tension, because your predictive model of the moment was interrupted. The world's meaning, for you, is built entirely from the dance between expectation and surprise. It's a strange thought. The universe you inhabit isn't out there waiting, fixed and detailed. It's constructed moment by moment, sculpted from a thin layer of sensory data and thick layers of interpretation. What you call the world is the surface of an agreement between your biology and the environment. You sense only what both sides can afford to share. Philosophers sometimes call these useful fictions. The table you rest your hand on, the sky, the colour red, all are stable metaphors, evolved and refined through millions of years of perception. They are not lies exactly, but they aren't literal either. They are negotiated truces between chaos and comprehension. The physical universe might be endlessly complex, but our senses provide a version tuned for survival. A simplified, user-friendly interface that hides the wiring. When you think of it this way, even the boundaries you take for granted, between inside and outside, past and present, begin to soften. Perhaps space and time themselves are part of this interface. They feel fundamental, but maybe they're not the source code, just the coordinate grid the brain uses to keep the story organized. If that sounds far-fetched, remember, every sensory dimension you experience, from color to sound to texture, is an invention of neural translation. Why should time and space be any different? Modern physics quietly agrees. The deeper we look into the nature of reality, the more the basic stage of space and time begins to flicker. At the smallest scales, they dissolve into uncertainty, and their structure depends on how they're observed. That realization will carry us soon beyond psychology and into quantum mechanics, where even particles seem to wait for observation before deciding what to be. But for now, imagine the universe as a grand interface, one that adapts itself to every observer. Each consciousness opens a slightly different window, translating the same underlying information into a personal world. The moon, the table, the sound of a loved one's voice, each feels solid, yet all are woven from patterns of probability and perception. Perhaps then, reality is less like a stage filled with objects, and more like a shared performance that needs participants to stay alive. The world we experience is not the raw world. but its gentle translation, a moving mirror polished by biology and shaped by the need to act, to survive, to find beauty. If we follow the thread a little further, we arrive at a provocative thought. Evolution itself may have chosen this simplification on purpose. The organisms that soar truly might have perished, while those who soar efficiently thrived. In that light, perception's limits are not defects, they're the price of existence and the secret to its persistence. Our quiet exploration now turns toward that idea, toward the mathematics that suggests truth is not what nature rewards, and that the creatures who see the world most clearly may be the first to vanish. Imagine two creatures living side by side on an ancient plain. One of them sees the world as it really is, every detail of light scattering through the air, every vibration of a leaf, every precise wavelength of sunlight reflecting from stone. The other sees less. Its vision is crude, simplified, more like an impressionist painting than a photograph. It can't tell one hue of green from another, and it doesn't notice the fine structure of shadow. But it knows which shade of green usually means food, and which dark patch might hide a predator. When a storm rolls in, the first creature studies the shapes of the clouds and the optical geometry of light refraction. The second just runs for shelter. You already know which one survives. This is the essence of what Donald Hoffman calls the fitness beats truth principle, a quiet revolution in how we understand perception. In the mathematical models he and his colleagues developed, organisms that perceive reality accurately tend to lose the evolutionary race. Their attention is spread too thin, wasted on details that don't matter to survival. Meanwhile, creatures that perceive only what's useful, a drastically simplified version of the world, win. Evolution, in that sense, doesn't favour truth, it favours utility. You can think of this through a simple everyday metaphor, the dashboard of a car. When you drive, you don't see the engine, the pistons, or the flow of fuel. You see a few dials, speed, temperature, fuel level, just enough information to act effectively. The red warning light isn't a literal flame or a physical problem inside the metal. It's an icon, a signal. Its job is not to tell you everything, but to tell you just enough. Seeing the engine itself while you're driving would be distracting and dangerous. Evolution built our minds in the same way. The senses are dashboards, not windows. And so colours, sounds and textures are like icons on that dashboard, simplified representations of vast physical processes. The redness of an apple isn't a property of the fruit itself. It's how your brain translates certain wavelengths of light, roughly around what scientists would call 670 nanometers, into a sensation you can act upon. But instead of numbers and nanometers, you get red, a feeling of ripeness, sweetness, reward. Evolution learned that creatures who see red eat the apple. Those who pause to calculate electromagnetic frequencies do not. This isn't to say reality is arbitrary. It's to say that what you perceive is tuned, not true, like a radio receiver built to catch only the frequencies that keep you alive. The rest of reality hums on all around you, unheard. Even pain and pleasure, those most intimate sensations, follow the same logic. Pain doesn't show you damage, it shows you danger. It's a signal designed to alter behaviour, not reveal truth. The burning of a stove tells you to pull your hand away long before the cells are destroyed. Evolution's message is clear. To live, one must feel enough, not everything. You can trace this principle through the history of life itself. The bat's sonar, the shark's electrosense, the bird's navigation by magnetism. Each is a tiny custom-made interface, a narrow window through which the creature meets its world. None of them sees reality in full. Each sees just enough to thrive. And humans, despite our intelligence, are no different. We don't perceive quantum waves or space-time curvature directly. We perceive colours, faces, movement, warmth. things evolution cared about. This realization might sound humbling, but it's also freeing. It means our limitations are not failures of perception, but features of design. If we could see the full truth of reality, all its dimensions, all its microscopic chaos, we'd be paralyzed. Every decision would drown in data. We survive because we're blind to most of what exists. Hoffman's mathematical models, when simulated, make this point vivid. In these virtual ecosystems, creatures compete for resources. Some see the environment accurately, mapping every detail. Others see only what correlates with fitness, a tiny subset of the truth. After many generations, the accuracy seekers vanish, and the efficiency seekers dominate. In other words, nature edits perception the way a novelist edits a story, cutting everything that doesn't move the plot forward. And this editing has shaped not only how we see, but how we think. The brain's internal language evolved for prediction and action, not for describing the universe's ultimate structure. We inherited a mind good at guessing what will happen next, not one that knows what reality is. Even our sense of time may be part of this interface, an ordering of events that helps us survive, not a fundamental property of the cosmos. When you press your hand against a wall, it feels solid. Yet physics tells us it's mostly empty space, with electric fields preventing atoms from merging. Your senses don't show you the truth of quantum repulsion. They show you the experience of resistance, a symbol for you cannot pass through. In the same way, the warmth of sunlight on your skin isn't the direct touch of photons, it's your biology translating energy into comfort. The dashboard glows, the signal is understood, and you live another day. But there's a subtle irony here. The more science uncovers about the world, the more it seems to validate this idea. Physics itself now describes a universe where the things we once thought solid are merely patterns of probability, where even space and time appear to be emergent, and where observation plays a curious role in bringing potential into presence. It's as if, beneath the surface of our evolved interface, reality itself behaves according to similar rules, compressing, simplifying, rendering information into appearance only when needed. Perhaps that's the grand joke of existence, that even the universe might be practicing its own kind of evolutionary efficiency, not showing every detail at once, but revealing only what's relevant to the moment. What we call laws of nature could be the high-level icons of a much deeper system. And if that's true, then physics doesn't describe reality as it is. It describes the interface's rules, the elegant patterns that govern what appears when we look. We've mistaken the beauty of the design for the depth of the thing itself. But that mistake has given us everything: art, science, technology, wonder. It's worth pausing here in this quiet reflection to feel what that means. Every colour you've ever loved, every taste, every touch, all a part of the same survival interface. And yet, through this limited window, something extraordinary has happened. Consciousness has become aware of the illusion. The dreamer has realised they're dreaming. And that realization opens the door to questions evolution never planned for. If perception is an interface and not a mirror, and if even our best instruments only refine that interface rather than escape it, then where does the boundary between observer and observed truly lie? Are we seeing the universe, or is the universe seeing itself through us? As we drift further into the story, we step beyond biology and into physics, the domain where observation itself stops being metaphor and becomes law, a place where reality, under experiment's gentle gaze, begins to tremble like a curtain touched by light. Picture a quiet laboratory late at night. There's a faint hum of machines, the gentle flicker of a monitor, and on the table, a small apparatus, simple enough that it could almost fit in your hands. A beam of light or a stream of electrons is sent toward a screen with two narrow slits cut into it. The setup looks harmless, like a school experiment in a miniature. Yet what it reveals is one of the most unsettling truths ever uncovered, that reality itself may hesitate to exist until it's asked to. This is the famous double-slit experiment, the place where the story of modern physics begins to whisper something impossible. When we send particles, tiny bits of matter, like electrons, one at a time through the slits, they act like waves. They spread out, overlap, and create rippling patterns on the back screen, a soft dance of light and shadow, like waves of water crossing a pond. But if we try to watch which slit each particle goes through, if we install a tiny detector to check its path, the wave pattern vanishes. The particles stop behaving like waves and march through one slit or the other, as though the act of observation has forced them to decide who they are. It's as if the universe plays with possibilities until someone looks, and only then chooses a story. Before the measurement, each particle is described not as a single point, but as a cloud of potential, a range of places it could be, like a soft fog of probability. Physicists call that mathematical fog the wave function, but instead of using that phrase, imagine a song not yet played, all notes possible, none yet chosen. When the observer measures, the song begins. The universe commits to a single melody, and the other possibilities fade into silence. This doesn't mean consciousness magically controls matter. That's a common misunderstanding. What it shows is that observation and existence are bound in a delicate relationship. The experiment doesn't need human gaze, even a simple detector will do. What matters is that information has been recorded, that the universe, in some small way, has been forced to declare an outcome. The effect feels personal because it echoes the theme we've carried from perception and evolution, that what we experience as solid reality may be more like an interface, a behaviour that arises when interaction occurs. The world doesn't present itself all at once, it responds. To grasp this without equations, imagine flipping a coin, but the coin doesn't land until you look at it. For as long as you turn away, it hangs in superposition, both heads and tails at once. When you glance back, it settles, as though the act of checking gave it permission to exist. The mathematics behind this is clear and precise, but the meaning is softly strange. Probability isn't just about ignorance, it's about genuine possibility waiting to be realized. When physicists like Niels Bohr and Werner Heisenberg first confronted these results a century ago, they struggled to explain them without breaking the logic of cause and effect. Bohr proposed that the world of atoms simply doesn't have definite properties until measured. Heisenberg's uncertainty principle followed from that idea, not a formula to memorize but a truth to feel, that knowing one aspect of something precisely means letting go of another. Nature doesn't allow full possession of its secrets. This uncertainty isn't a flaw, it's the texture of reality itself. The more deeply you try to pin it down, the more it slips through your fingers. You can know where a particle is, or how fast it's moving, but not both with absolute precision. It's like trying to describe a candle flame in motion. The more you focus, the more your attention itself disturbs the dance. Einstein never accepted this. He once wrote to a friend, "God does not play dice with the universe." Bohr famously replied, "Stop telling God what to do." Their disagreement wasn't really about theology. It was about whether the world exists independently of observation. Einstein wanted a universe that was always there, definite and complete, even when unseen. Bohr believed the act of measurement is part of what defines what is. A century later, the data side with Bohr. The coin waits to land. And yet, as unsettling as it is, the double-slit experiment carries a certain quiet beauty. It suggests that potential and actuality are not enemies, but partners. The universe holds its breath in a superposition of maybes until an interaction crystallizes it into now. This isn't mysticism. It's just how nature behaves when you look closely enough. We live in that dance every day, though we rarely notice it. When you flip a light switch, billions of electrons leap through circuits guided by probabilities. When you read these words, photons bounce from your screen into your eyes, and each one carries the legacy of wave and particle, sometimes behaving as a smooth ripple, sometimes as a pinpoint of energy. The world works because of that ambiguity, not in spite of it. Some physicists describe the quantum world as a realm of potentialities. Others, like John Wheeler, call it the participatory universe. In his words, the act of measurement doesn't just uncover the world, it helps bring it into being. Wheeler liked to summarize this with a gentle phrase, it from bit. Every piece of matter, energy, or space arises from a bit, a fundamental act of yes or no information. If that's true, then the double slit experiment isn't just about electrons, it's about existence itself. It's about a universe that behaves more like a story unfolding through questions and answers than a static object sitting on a shelf. You can think of each measurement as the universe answering a small binary question, here or there, this or that, wave or particle. Each answer adds a brushstroke to the grand painting we call reality. And just like your own senses evolved to compress the world into useful information, perhaps the cosmos does the same, storing only the outcomes that matter, letting the rest dissolve back into possibility. If you stand under the night sky and imagine that the stars above are still in their many potential states until their light reaches your eyes, you might feel a small shiver, not of fear, but of wonder, that the simple act of observing connects you to something so fundamental, so participatory, that every glance becomes a dialogue with the universe. In the next step of our journey, we'll see that this strange dance doesn't end with electrons and slits. It continues with entanglement, when two particles once linked can echo each other's choices across the vastness of space, as if the fabric of reality itself remembers that they were once together. Imagine two tiny particles, born together in a moment of shared creation, perhaps from the same burst of energy, the same flicker of light. Then imagine sending them drifting to opposite ends of the galaxy. One particle ends up in your lab on Earth, the other on a lonely satellite orbiting a distant star. Now, in that cosmic silence, you reach out to measure the one near you. Instantly, you learn something about the other, even though no signal has passed between them. No messenger has had time to travel. Somehow the two behave as if the universe itself forgot that distance existed. This is entanglement, the quiet thread that connects things once joined. No matter how far apart they drift. It's not a metaphor, but an experimentally verified fact, first hinted at by Einstein, Podolsky and Rosen in the 1930s, and tested in exquisite detail ever since. Einstein disliked it. He called it spooky action at a distance, a phrase that captured both his curiosity and his discomfort. The idea seemed to violate the most sacred rule of classical physics, locality, the notion that nothing can influence anything else faster than light can travel. For decades, physicists debated whether entanglement was a real feature of the universe or just a trick of incomplete information, hidden variables we hadn't yet discovered. Maybe the particles simply carried secret instructions when they parted ways, prearranging their responses. It was a comforting thought, the kind of tidy explanation that made the world feel mechanical again. Then, in the late 20th century, John Bell devised a mathematical way to test that idea. Without diving into formulas, imagine it like this. If the particles really were obeying local hidden rules, there would be strict statistical limits to how correlated their behaviours could be. But if the universe truly allowed a kind of deep, non-local connection, something beyond classical logic, those limits could be broken. And so experiments were built, detectors aligned, photons entangled and measured. Each test tightened the conditions, closing possible loopholes. Finally, in 2015, a team led by Ronald Henson in the Netherlands performed what's called a loophole-free Bell test. The result: the correlations exceeded the classical boundary. The secret instructions weren't there. Local realism, the comforting idea that things have definite properties, independent of measurement and separated by distance, had quietly crumbled. In plain language, nature doesn't play by the old rules. When two particles are entangled, they form one shared system, even when light years apart. Changing one doesn't send a signal to the other. It's more accurate to say there's nothing between them to send. Their properties aren't two halves communicating. They're one whole being expressed in two places. To visualize this without numbers, think of a pair of gloves, one left, one right. If you separate them and find a left glove in your drawer, you instantly know the other is right. That's classical correlation, simple logic, but entanglement is different. Before you open the drawer, neither glove is defined. Both are in a hazy state of possibility. Only when you look does the pair together settle into a definite pattern, no matter how far apart they are. It's as if the universe waits for your peek before deciding which hand each belongs to. This is what physicists mean by non-locality. It doesn't mean faster-than-light communication or magic telepathy. It means that the universe's bookkeeping doesn't respect our human notion of separation. Space, at the quantum level, isn't a grid of isolated dots. It's a web of relationships. The connections are what's real. The distances may be what's emergent. Carlo Rovelli, one of the thinkers who helped formalize this view, calls it relational quantum mechanics. In this interpretation, facts exist only relative to observers. There isn't one global reality floating above all others, just many intertwined perspectives. When you measure something, you're establishing a relation between your system and the one observed. Another observer, watching from elsewhere, might describe that relation differently, and that's fine. Reality is the network of all such relations, not a single absolute stage. That may sound abstract, but it fits beautifully with our earlier reflections on perception. Each of us sees the world through an interface built for survival, a user-specific version of reality. Quantum physics seems to echo that principle at a fundamental scale. Existence itself might be relational, a tapestry of interactions rather than a collection of self-contained objects. The universe behaves less like a machine and more like a conversation. To bring this down to something tangible, picture two musicians playing across a vast field. One plucks a string, the other strums, and somehow their notes remain perfectly harmonized, though no sound could have crossed the distance in time. The harmony isn't transmitted, it's shared, like an invisible rhythm that both are following. Entangled particles follow a cosmic rhythm of that kind, a deeper beat woven through the structure of reality. Einstein found this unbearable because it undermined his sense of an objective universe that exists whether or not anyone looks. But to many physicists today, that loss of objectivity is not chaos, it's connection. The boundaries between things soften, and we begin to see reality as an ocean of correlations, where every measurement is a small ripple spreading through a seamless whole. It's hard to shake the human intuition that space separates, that one event here and another event there must be distinct. But entanglement whispers a different story. It says space may only be an approximate description, a large-scale illusion of independence. At the deepest level, what matters is not where things are, but how they relate. And so, when the two entangled particles choose their states in perfect coordination, defying any local explanation, the universe isn't breaking its own speed limit. It's reminding us that distance might not be what we think it is. Perhaps there's a level beneath geometry itself where everything is fundamentally linked, not through hidden wires, but through shared information. This isn't just philosophy. Quantum entanglement is now used in real technology. Quantum encryption, teleportation of information, and the first steps toward quantum computers. The very weirdness that once seemed mystical is now being engineered into circuits and algorithms. Our devices exploit the same non-local coherence that puzzled Einstein. There's a strange humility in that. Humanity doesn't just study quantum mechanics. We're beginning to collaborate with it. We've learned to whisper in the language of probability and correlation, and the universe ever so gently whispers back. Perhaps that's what the Bell experiments ultimately revealed. Not that reality is broken, but that it's bigger than our expectations. The local, isolated view is always a convenient story. The truth is woven, continuous, and alive with relation. If we follow the thread a little further, we find another kind of mystery waiting. Experiments where the very act of choosing how to measure can reach backward, reshaping what seemed already decided. A world where time itself, like space, may not be as straightforward as it appears. Imagine standing in a quiet room where a beam of light splits and travels down two paths. One path winds through a set of mirrors, the other through a crystal that can twist a photon's properties. Both routes eventually meet again at a screen, where their waves overlap and form a delicate pattern, bright and dark fringes like ripples from two pebbles thrown into the same pond. You might think the pattern is fixed once the photons have passed. But what if, after all that, you decide to ask a question the universe thought you had already forgotten? This is the essence of the delayed choice quantum eraser experiment. It's a variation of the double-slit setup, but with a twist so elegant that it almost feels like mischief. Photons are sent through the apparatus, and after they've already hit the detector, scientists decide whether to measure information that would reveal which path they took. The astonishing result is that the interference pattern, the sign of their wave-like behaviour, depends on that later choice. When we choose to know the path, the interference disappears. When we choose to erase that knowledge, the pattern reappears, even though the photons have already finished their journey. It's as if reality looks backward to stay consistent with what's been learned. The cause seems to follow the effect, and the arrow of time bends into a loop. Of course, nothing literally travels to the past. The mathematics simply shows that until the entire experimental chain is complete, until all correlations are settled, the story of the photon isn't finished. The measurement doesn't change what happened. It defines what counts as having happened. You can think of it this way. The universe is like a book being written as it's read. The words appear in order, but the meaning of each chapter can depend on the ones that follow. Observation doesn't rewrite the past, but it does finalize which version of the past becomes real. In this strange storytelling, the reader and the author are the same. The delayed choice experiments are often accompanied by a quieter phenomenon called the quantum Zeno effect, named after the philosopher who imagined an arrow frozen mid-flight. In quantum physics, if you continuously observe a system, say an unstable atom that's about to decay, the very act of watching can prevent the change from occurring. It's as though under a constant gaze the universe hesitates to move. Physicists sometimes describe it as a watched kettle never boils, brought to life in the subatomic world. Continuous measurement freezes the motion it tries to track. The reason lies in how quantum systems evolve. Not smoothly, but through probabilities. Each unmeasured moment allows the wave of possibilities to spread and evolve naturally. Measurement collapses that spread into a specific outcome. So if you measure often enough, you keep forcing the system back to where it started, never giving it time to unfold. It's not magic. It's the way the mathematics of probability behaves when observation is relentless. Translated into softer language, it means the universe prefers a bit of privacy. Taken together, these two effects, delayed choice and the Zeno pause, suggest something profound. Observation is not passive. It doesn't merely reveal the world, it participates in it. The act of asking a question changes what can be answered. Every measurement is both a spotlight and a sculptor. This is where physicist Wojciech Zurek's idea of quantum Darwinism comes into the picture. and it carries the same evolutionary flavour we've already seen in perception. Just as natural selection favours the traits that survive repeated encounters with the environment, quantum Darwinism proposes that only certain states of a quantum system survive repeated observation. When particles interact with their surroundings, photons, air molecules, detectors, some of their properties become redundantly recorded, copied into the environment again and again. Those are the properties many observers can agree on. They form the stable world of classical reality, the one where tables stay solid and coffee mugs don't vanish when you look away. In this view, the classical world we live in isn't an illusion that breaks under scrutiny. It's the most robust pattern of all, the one that survives countless acts of observation. You might say reality is what remains when everything else has been measured to death. It's the fittest illusion, the one stable enough to persist across all viewpoints. It's humbling to think that the same logic guiding evolution, survival of the stable, may also guide the birth of everyday reality. The moon doesn't depend on any one observer to exist. It's observed constantly by sunlight, cosmic rays, and the fabric of space itself. Its existence is redundantly encoded, reinforced at every moment. You and I are simply two among many witnesses reading the same record. Still, that record begins with a fragile process. At the smallest scales, before the environment's relentless copying begins, reality is fluid. A photon undecided, a particle halfway between possibilities, a faint hum of probabilities waiting to settle. Observation doesn't destroy that fluidity. It's the process through which fluidity becomes form. The act of watching is the universe declaring a moment complete. We can feel echoes of this in ordinary life. Think of an idea you've kept private for a long time. A dream, a fear, a story you haven't told. The moment you speak it aloud, it becomes something else. Real, solid, part of a shared world. Observation is like that. Before it's spoken, reality is thought. After it's observed, it's fact. The delayed choice experiments and the quantum Zeno effect show that even our most fundamental notions of time and cause are not as fixed as we assume. The universe is not a film reel unspooling in one direction. It's a web of interdependent events, each giving context to the others. The flow of time, as we feel it, might be an emergent story told by the accumulation of observations, a narrative woven from countless acts of noticing. And perhaps that's why the quantum world feels so alien. It's not that it's foreign to us, it's that we've been reading only the final draft, the version already edited by countless acts of cosmic proofreading. Beneath that familiar text lies a restless manuscript of maybes, forever being revised by observation. So when we say watching changes the watched, it isn't a metaphor for human curiosity. It's a literal description of how the universe operates at its foundation. Every interaction, whether it's a photon hitting a mirror or a thought rising in a mind, is an event that refines possibility into presence. If we follow the thread a little further, that foundation becomes even stranger. Beneath the dance of observation and measurement, beneath the apparent particles themselves, lies something even more fundamental. A hidden ocean of fields. In that ocean, everything that seems solid or separate turns out to be a ripple. Close your eyes for a moment and imagine the smallest thing you can think of. Perhaps a speck of dust floating in a sunbeam, or the faint shimmer of pollen caught on a breeze. Now try to picture something smaller still. An atom, a proton, a single electron spinning around its invisible orbit. Most of us, when we imagine these things, picture tiny spheres, like microscopic marbles rolling inside one another. It's a comforting idea, solid, neat, something you could hold if only your fingers were small enough. But the deeper science has looked, the more that picture has quietly fallen apart. The universe, it turns out, isn't made of marbles, it's made of music. This idea didn't arrive all at once. It crept in through experiments and mathematics that refused to behave. When physicists measured electrons colliding or photons scattering, The results didn't fit a world of hard, separate particles bumping like billiard balls. The numbers only made sense if each so-called particle were understood as a ripple, a small disturbance in a vast continuous medium. Imagine a calm ocean stretching endlessly in every direction. Drop a pebble into it and you get a ripple that moves outward. The water itself isn't travelling with the wave, only the vibration is. Quantum field theory, the framework that replaced the old particle picture, says reality works the same way. Every kind of thing, electrons, photons, quarks, even the forces that pull and push them, is a vibration of a corresponding field that fills all of space. Those fields are everywhere, even where you think there is nothing. Physicist David Tong likes to describe it like this: the universe is made not of dots, but of oceans. Electrons are the ripples in the electron ocean. Light is the shimmering surface of the electromagnetic sea. What we call matter and energy are simply different patterns of vibration in these invisible waters. It's a radical thought, but a beautiful one. Solidity, that reassuring sense of something being there when you knock on a table or grip a coffee mug, is not the result of tiny balls packing together tightly. It's the result of synchronized vibrations. Your hand and the table are both excitations of their respective fields, and what you feel as contact is the resistance of one pattern meeting another. Like two overlapping waves that refuse to merge, their interference creates the sensation of firmness. We live, quite literally, inside a song made of standing waves. To make sense of this without equations, think of an orchestra tuning before a performance. Each instrument plays its own note, and as the sounds overlap, patterns emerge. Chords, harmonies, beats. Those patterns fill the room with richness, even though the air molecules themselves only vibrate back and forth by the tiniest amounts. The music doesn't exist in any one instrument. It exists in their relationships. In the same way, an atom isn't a miniature solar system of orbits. It's a stable chord formed by the interplay of vibrating fields. In everyday life, we take those harmonies for granted. The chair you sit on doesn't seem to hum with cosmic rhythm. But deep down, it does. The fields that create matter never rest. Even in absolute zero temperature, where motion seems to stop, the fields still quiver faintly. Physicists call that ever-present vibration zero-point energy, but you can think of it more softly as the universe's background hum, a lullaby that never ends. It's difficult to overstate how thoroughly this field view replaces the old idea of particles. In the equations of quantum field theory, or to put it in gentler language, in the logic of the model, there are no separate objects moving through emptiness. There's only the field, shifting its own internal melody from place to place. A particle is just the brief appearance of one note within that endless symphony. When two particles collide, what really happens is that their ripples overlap and interfere, exchanging energy, changing tempo. They don't bounce, they resonate. The apparent solidity of matter emerges from the mathematics of overlapping vibrations. Patterns upon patterns, each reinforcing the next until something durable appears. This picture of the world feels less mechanical and more alive. Instead of a universe of cold fragments, we have one continuous fabric, more like a piece of silk than a pile of sand. Everything touches everything else, if only faintly, through the gentle continuity of its field. Even empty space is part of the same fabric. You might wonder why we ever believed in particles at all. The answer lies in how our instruments, and our instincts, work. We perceive discrete hits, a flash on a detector, a dot on a screen. Our eyes and tools translate continuous vibrations into individual events, because that's how information arrives to us. It's a kind of pixelation of the infinite, but beneath those pixels the smooth wave remains. Once you start thinking this way, the universe becomes a very different place. The stars above, the light from your lamp, the warmth of your breath, All of them are field excitations, energy temporally shaped into forms that can meet, exchange, and move on. You and I are ripples in the same sea, patterns of vibration that happen, for a brief while, to sing in harmony. It's a perspective that can feel both intimate and infinite. Intimate because it erases the boundaries between things. The chair, the hand, the air, and the voice reading these words are all part of one continuous medium. Infinite because the field has no edges, no gaps where reality stops. The cosmos is full, even where it looks empty. In this view, the death of the particle is not the end of solidity, but the beginning of understanding. What we lose in tiny marbles, we gain in connection. The universe is less like a warehouse of stuff and more like a composition, a delicate, never-ending performance that plays itself into existence. And perhaps that's why it feels so natural to find music soothing. Somewhere deep in us, at the level of physics itself, everything that exists is vibration, rhythm, resonance, and tone. To listen to a melody is to hear a small echo of what the world has been doing since the beginning, oscillating between possibility and presence, wave and form, silence and song. If we drift further into the story, we find that this ocean of fields doesn't stay still. Even when nothing seems to happen, it stirs, alive with flickers and fluctuations, tiny borrowings of energy that never quite go away. It is the restless sea beneath the calm surface we call nothing. Try for a moment to imagine perfect emptiness. No dust, no air, no light, just nothing. The mind immediately tries to paint that scene, a black void perhaps, or a dark room without sound. But even that picture is already too full. Darkness is still something you can see. Silence is still something you can hear. Real emptiness, the kind physics speaks of, has no colour, no temperature, no boundary at all. And yet, even that imagined void is not truly empty. According to quantum field theory, what we call nothing is actually the most crowded place in existence. Beneath the calm surface of space lies a restless ocean of energy. Fields don't vanish when matter is gone, they stretch infinitely, filling the universe. Even between stars, even in the hollow space between atoms, these fields remain, shimmering with subtle activity, always on the edge of motion. If you could somehow float there, in the deepest cosmic vacuum, you wouldn't find stillness. You'd find motion too, small to measure, vibrations too quick to follow, energy flickering in and out like breath. These are not poetic inventions. They're measurable effects of what scientists call zero-point energy, the baseline hum of every field, the energy that remains even when all else is stripped away. Of course, when physicists write this out, they use mathematical terms like vacuum fluctuations, but you don't need equations to feel the image. Imagine a calm ocean at night. To the eye, the surface looks flat and mirror smooth, but if you listen closely, you can still hear the faint hiss of water shifting, tiny ripples forming and fading before they ever grow into waves. That's the quantum vacuum, a sea so balanced that its activity cancels itself out, yet never quite stops. Sometimes, under the right conditions, that quiet background reveals itself. One of the most delicate proofs came from the Casimir effect, an experiment that seems almost like a magic trick. Two uncharged metal plates are placed incredibly close together, separated by just a few hundred atoms width. In that narrow gap, the energy of the vacuum behaves differently. Certain wavelengths of field vibration fit between the plates, others don't. The imbalance creates a subtle pressure that pushes the plates together, as if invisible hands were squeezing them from the outside. It's not that a mysterious force appears out of nowhere. It's that the nothing between the plates is slightly less active than the nothing around them. The difference becomes a touch, a measurable attraction. Some physicists describe it as the plates whispering to the vacuum, coaxing it into revealing that it was never truly still. You might wonder, if empty space is so alive, why doesn't the universe explode with energy? Why don't we see this vibration everywhere? The answer lies in balance. The quantum fields fill every corner equally, their opposing fluctuations cancelling in exquisite harmony. It's like a vast orchestra tuning in perfect symmetry. Every note answered by its mirror, every sound instantly resolved into silence. Only when that balance is disturbed, by boundaries, fields, or measurement, does the quiet hum become something we can touch or see. There's a certain elegance in that idea. Creation as disturbance, existence as a small ripple on a background of balance. From this perspective, nothingness is not the absence of being, it's the womb of being. It's a potential so complete that even the smallest tremor gives rise to something. The ancient philosophers who once called the void chaos were not entirely wrong. It isn't a dark emptiness, but a boundless potential, an ocean whose stillness hides unimaginable depth. You might have noticed that this sounds oddly spiritual. The notion that what we call nothing is alive, that the universe is full even when it seems bare. But this isn't mysticism, it's physics. The evidence shows, up in every experiment that probes the vacuum, the Casimir effect, the Lamb shift, the way atoms behave in near-perfect cold, all trace back to the restless fields beneath existence. In this sea of constant fluctuation, virtual particles appear and vanish endlessly. Virtual doesn't mean imaginary, it means fleeting. They're tiny disturbances borrowing energy from the field, existing for a heartbeat before returning it. The borrowing is permitted by the rules of quantum uncertainty, not a strict equation, but a soft balance between energy and time. If the loan is small enough and repaid quickly, the universe allows it. These ephemeral particles pop in and out, filling space with a quiet fizz of creation and return. Sometimes, those brief flickers have cosmic consequences. During the earliest moments of the universe, when everything was compressed into a point of almost infinite energy, these quantum fluctuations were amplified, frozen into the structure of space itself. The galaxies we see today, clusters of stars and worlds, may trace their origin back to those first tiny ripples in the vacuum. The largest patterns in the sky are, in a way, echoes of the smallest whispers in nothingness. So when you look up at night and see the stars scattered across the dark, remember that the darkness between them is not empty. It's the same fabric that gives birth to light. The space between stars, between atoms, between thoughts, is the background sea from which all things arise. If this sounds poetic, that's because reality at this level almost demands poetry. Words like energy, field, and vacuum are only shorthand for processes too intricate for language. What matters is the feeling they evoke, a sense of quiet abundance, of something infinite moving beneath the ordinary. The next time you see a shadow or feel a breeze, think of it as the visible tip of an invisible ocean. Physicist Richard Feynman once remarked that even if everything we know vanished, every particle, every planet, every beam of light, the fields would remain. They are the true substance of reality. The emptiness that surrounds us is not a void to fear, but the most generous thing of all. It holds everything that was, everything that is, and everything that could ever be. And as strange as it sounds, it is the instability of this nothingness, its refusal to stay still, that allows there to be a universe at all. Out of the gentle imbalance of that cosmic sea, creation continues to ripple outward, moment by moment. If we drift further into this story, we'll begin to see how those ripples combine, how the music of fields becomes the architecture of matter, how vibrations knit together into the shapes and textures that fill our lives. Close your eyes for a moment and imagine standing on the shore of a vast moonlit sea. The waves are small, almost invisible, but their rhythm is steady. If you listen, carefully you can hear them forming subtle harmonies, each crest folding into the next, overlapping, colliding, merging. Now imagine that those ripples could somehow weave themselves into forms, into sand, into shells, into you. That's not just poetry. In the physics of our universe, that's almost exactly what happens. From the gentle trembling of the quantum fields, those endless seas that fill all of space, comes everything. Every atom, every colour, every heartbeat, every thought. The ripples don't just exist, they interact. And those interactions create patterns, stable patterns, things. When two waves meet, they can amplify or cancel each other. Musicians know this as harmony and dissonance. Physicists call it interference. Picture two stones dropped into a pond at slightly different spots. Where their ripples meet, some peaks grow taller, others vanish into flat calm. At the microscopic level, the same principle rules the universe. The fields of matter, light, and force cross paths, and in their meeting, reality acquires texture. Think of the electron, that tiny carrier of electric charge. In one sense, it's just a ripple of the electron field. But when it moves through the electromagnetic field, it creates a complex pattern, one that gives rise to electricity, chemistry, and life itself. The interaction is not a collision between objects, but a duet between vibrations. What we call forces are the rhythms by which fields communicate. When the vibrations become stable, when their interference patterns repeat, something new appears. That's how atoms exist. The electron field hums around a nucleus in a repeating standing wave, like a note that refuses to fade. The shape of that wave determines the element's properties: hydrogen's simplicity, carbon's flexibility, gold's soft glow. Each atom is a unique pattern of resonance. You can feel these resonances in the world around you. The warmth of sunlight, the blue of the sky, the solidity of a rock. All are the visible consequences of invisible patterns. Photons interacting with electrons, waves combining and cancelling in ways that the eye interprets as colour and the hand as touch. There are no hard edges, only regions where certain rhythms dominate. To make that idea more tangible, imagine a single note played on a violin. By itself, it's beautiful but simple. When joined by other notes, the cello's depth, the flute's clarity, harmony emerges. Out of pure vibration, you begin to sense something like structure, even emotion. That's how atoms and molecules behave. When their fields resonate together, they form the chords of matter. And when many chords combine, they produce the melody of the physical world. Even solidity is just resonance. When you press your hand against a table, what stops it from passing through isn't a wall of substance, but the balance of electromagnetic vibrations. The electrons in your hand, as in the table, repel each other, not because they are solid, but because their fields overlap in ways that cannot coexist. The result feels like firmness. The sensation is real, but the mechanism is rhythm. It's almost impossible not to find that poetic, that what we call things are more like notes held in a song than pebbles in a jar. If you could somehow turn off the music, still the fields, silence the waves, everything would vanish, leaving only the quiet potential of the ocean beneath. This realization changes how we might think about identity. If every piece of matter is a pattern of vibration, then so are we. The atoms in your body, once part of ancient stars, still hum to the same cosmic tune. You're not separate from the fabric of the universe. You're one of its melodies, briefly played, endlessly interconnected. Even space itself may not be the ultimate background, but another kind of pattern. Some physicists suspect that space and time emerge from the collective behaviour of fields and entanglement, that geometry, distance, even the sense of here and there are harmonies formed by deeper relationships. Just as music can fill a room without occupying physical space, the fields may generate space-time as a larger composition, the stage created by their own performance. You can sense the intuition behind this without equations. When you listen to a symphony, you don't think of air molecules oscillating, you hear the melody as a whole. The physics of sound gives rise to the experience of music. Perhaps in the same way the physics of fields gives rise to the experience of the world. The melody is real, even if the notes are fleeting. This perspective also reshapes our notion of creation. We often imagine the birth of the universe as a moment when something emerged from nothing, an explosion filling emptiness with matter. But if the fields are fundamental and always present, then creation may be less an explosion and more a change in harmony, a shift from silence to song. The cosmos began not with a bang, but with the first note of a composition that has been unfolding ever since. In this view, what we call laws of physics are like the musical scales of the universe, patterns of possibility that decide which chords can form. When you strike a piano key, you don't create sound from nothing. You awaken a note that was always available within the instrument. Likewise, when reality forms atoms, stars, or consciousness, it may simply be exploring the resonant possibilities of its own nature. There's a quiet beauty in realizing that even the most ordinary objects around you, a spoon, a window, the air, are frozen music, patterns too slow for us to hear. You live surrounded by harmonies, each atom humming at its own tempo, each interaction a tiny duet in the endless composition of being. And in that endless composition, there's motion as well as memory. Every vibration carries information, a record of its past interactions. The universe, through its overlapping waves, remembers itself. When those vibrations combine in complex ways, forming molecules, cells, and brains, memory becomes conscious. The field learns to listen to its own song. Perhaps that's what awareness is. The universe vibrating in patterns complex enough to reflect upon themselves. A ripple looking back at the ocean and recognizing its own motion. If we drift further into the story, that idea leads us naturally toward a deeper mystery. What if the entire cosmic symphony, all these ripples and patterns, could be recorded on a surface? What if everything inside the ocean could be described by the vibrations on its edge? Imagine, for a moment, drifting near a black hole. Not falling in, just close enough to feel its gravity tugging at the edges of your thoughts. Space itself seems to bend, light stretches and curves and time slows until every second feels thick and syrupy. You watch a star's glow spiral inward, vanishing at the edge of that darkness, and you wonder, when something falls in, where does its story go? For most of the 20th century, physicists believed black holes were the ultimate erasers, cosmic drains swallowing everything, matter and memory alike. Anything that crossed the event horizon, that invisible boundary where gravity's pull becomes inescapable, was thought to vanish forever. Not just its atoms, but the information describing them, every pattern of light, every detail of structure, every whisper of identity. In the equations of general relativity that seemed final. But then, in the 1970s, two scientists, Jacob Bekenstein and Stephen Hawking, noticed something unsettling. A black hole, they realized, might not be entirely silent. It could have a temperature. That meant it could radiate energy, slowly, faintly, but surely, like a dim ember cooling over eternity. Hawking showed that this radiation arises because of quantum effects near the event horizon, where pairs of virtual particles constantly pop in and out of existence. Sometimes, one of the pair falls in while the other escapes. The escaping one becomes real, carrying energy away. The discovery was breathtaking, but it came with a paradox. If black holes can evaporate, and if they truly erase all information about what falls in, then when the hole finally disappears, the information is gone too. That would break one of the most sacred principles in physics. That information can never be destroyed, only transformed. Nature, it seemed, had committed an impossible crime. It was Bekenstein who first noticed another clue. one that quietly changed the shape of physics. He found that a black hole's entropy, a measure of its hidden information, doesn't scale with its volume as one might expect. Instead, it scales with the area of its surface. In simple words, the amount of information a black hole can contain is proportional not to how much space is inside it, but to how much surface area it has. That realization was astonishing. In everyday experience, the more volume something has, the more it can hold. A large jar holds more marbles than a small one. But in the strange world of black holes, the opposite seemed true. Information is written on the surface, like words etched into the cover of a book rather than the pages within. The black hole, far from being an eraser, was keeping a record, just not in the way we expected. Physicists began to whisper about a new principle, one so elegant that it sounded almost like poetry, the holographic principle. Just as a hologram encodes a three-dimensional image on a flat surface, perhaps the universe itself stores its information on boundaries, on the edges of space rather than its interior. You can picture this idea gently through analogy. Think of a photograph saved on a memory card. The card is flat, thin, and unassuming. Yet inside it lies the potential for entire landscapes. Mountains, faces, skies, sunsets. All of that detail exists not in the depth of the card, but in the pattern of charges on its surface. The black hole, in a similar way, might hold the entire story of what it has consumed on its horizon, written in light so fine we could never see it. In this view, the event horizon becomes less of a wall and more of a canvas. Each bit of matter falling in leaves a faint mark, a microscopic ripple in the surface record. The interior of the black hole becomes in a sense an illusion. The true bookkeeping happens on the boundary. Hawking himself was initially troubled by this. His own equation suggested that black holes radiate away energy randomly, erasing the past. But the holographic principle promised a gentler solution. Maybe nothing is ever truly lost. The information isn't destroyed, it's just encoded in a form too subtle for us to read. The implications ripple far beyond black holes. If information in one of the universe's most extreme environments can be stored on a surface, perhaps the same is true everywhere. Perhaps the world we experience as three-dimensional is actually a kind of projection, a rich image emerging from a two-dimensional layer of information beneath it. That might sound abstract, but the mathematics agrees. The surface area rule of entropy doesn't apply only to black holes. It seems to hold for any region of space when quantum mechanics and gravity meet. In every case, the total information inside a region never exceeds what can fit on its boundary. The cosmos, at its most fundamental, behaves as though it's made of pixels on a cosmic screen, each pixel representing a tiny bit of reality. This doesn't mean we live in a simulation, or that the universe is fake. It means that depth may be an emergent property, a way for information to express itself. The world feels solid, and that feeling is true for us, just as a holographic image looks three-dimensional, even though it's printed on a flat film. Our senses, tuned for the macroscopic world, experience the projection as the real thing. There's something quietly comforting about this. The laws of physics, once thought to be indifferent, suddenly appear to be meticulous record keepers. Nothing is forgotten, not even the light swallowed by a black hole. Somewhere, written on the fabric of space-time itself, the memory endures. If you stand outside on a clear night and look up, it's tempting to think of the stars as distant, solitary points, tiny fires scattered across emptiness. But if the holographic principle is right, then even that emptiness holds information. Every patch of space, every horizon, every unseen edge is carrying the universe's autobiography, written in patterns far too fine for our eyes. And so the black hole's whisper isn't one of destruction, but of conservation. It tells us that reality is careful, that nothing truly disappears. Energy becomes light, matter becomes vibration, and information becomes a kind of cosmic memory stored delicately on the surface of being itself. If we follow the thread a little further, this idea deepens. What if the holographic whisper of the black hole isn't unique? What if every region of space, even the one you occupy now, is part of that same correspondence? A hidden mirror between surfaces and interiors, between gravity and information. That's where our next journey leads, into a strange mirror world, where everything inside has a reflection written upon its edge. Picture the universe as a vast spherical room. Inside it, light drifts like dust caught in a sunbeam, and the air hums with faint vibrations. Everything you've ever known, planets, atoms, thought, lives within that glowing space. Now imagine that along the outer wall of this cosmic room is a mysterious film, so thin you can't touch it, yet it somehow holds the entire story of everything inside. Every event, every wave, every flicker of existence is written there, encoded in a language of light and connection. That is, in essence, the holographic principle extended to the whole cosmos. It was given mathematical shape in the late 1990s by a young physicist named Juan Maldacena. He proposed something quietly revolutionary, that a universe with gravity inside could be exactly equivalent to a world without gravity painted on its boundary. It's called the AD-CFT correspondence, though we can set those initials aside and think of it more simply as a mirror between two realities. In Maldacena's picture, everything that happens inside a region of space, stars being born, particles colliding, black holes forming, can be described just as well by information living on the outer surface. The inside and the outside are not separate worlds. They are two different ways of reading the same story. One speaks the language of space, time and gravity. The other speaks the language of quantum fields, vibration and information. It's a bold idea, but a surprisingly natural one once you've seen how black holes behave. The black hole's surface already hinted that information clings to boundaries. Maldacena's insight was to take that whisper seriously and ask, what if all of space-time behaves that way? You can imagine it like this. Think of an old-fashioned globe lamp made of glass. The world painted on its surface, the continents, oceans and islands, is a map, two-dimensional. But when the lamp glows, the patterns of light inside seem to create depth. The continents appear to float in space. The lamp's interior world is a projection of the data on its shell. We could in theory describe every ray of light, every shadow, using only the information written on that glass. In the same way, the universe might be a projection from its own boundary. We're not talking about illusion in the sense of being unreal. The projection is as real as the lamp's glow, but its source code may be written elsewhere, on the cosmic walls, in the language of quantum fields. One of the most elegant details of this correspondence is how geometry, the shape and curvature of space itself, seems to emerge from relationships of entanglement. Physicists Shinsei Ryu and Tadashi Takayanagi show that if you take two regions of the boundary and measure how entangled their quantum information is, the amount of connection you find corresponds precisely to the area of the surface linking them inside. In gentler terms, the stronger the connection between two parts of the universe, the shorter the distance between them. Space is not a static stage, it's a tapestry woven by correlations. That's a breathtaking thought. The closeness you feel between things may be the physical expression of information shared. When entanglement fades, distance grows. When it deepens, space itself knits tighter. The cosmos isn't made of matter scattered through emptiness. It's made of relationships so numerous and intricate that they become geometry. You can sense this intuitively. Think of a conversation with someone who understands you completely. Words are hardly needed. The exchange feels immediate. Distance irrelevant. Now imagine the opposite. A misunderstanding so wide that even across the same room, connection feels impossible. In a metaphorical sense, entanglement is the physics of understanding, the bridge across the quiet. The universe, then, is not a collection of things but a network of comprehension, held together by the exchange of information. This realization softens the boundaries between physics and poetry. When we say space is curved, we might just as well say space is shaped by connection. The gravitational pull that bends light and guides planets could be seen as geometry responding to information structure, a cosmic embroidery where every stitch is a quantum link. It's easy to get lost in the abstractness of it all, but there are gentle ways to picture it. Imagine a tapestry hanging on a wall. From afar you see depth, mountains, rivers, clouds, but as you step closer, you find it's all thread, a two-dimensional weave whose complexity creates the illusion of three. In the same way, the universe might appear three-dimensional to us because our senses walk through the fabric, tracing patterns that from another viewpoint lie flat. This perspective changes more than just physics. It changes what we mean by place. If space itself emerges from information, then where you are is defined by what you're connected to. Location becomes a matter of relationship, not coordinates. You exist where your links to the universe are strongest, where your pattern of entanglement resonates most vividly with the whole. There's a kind of quiet comfort in that. It means that isolation, in the deepest sense, is impossible. Even across unimaginable distances, every atom, every photon, every heartbeat participates in the same network. We are all written on the same wall, and if that's true, then perhaps within and beyond are not opposites, but reflections. The boundary and the bulk, the surface and the depth, are two languages describing one story. The story of information becoming form. Every breath you take, every beam of light from a distant star, is part of that story written in code too subtle for our eyes, but perfect in its consistency. It's astonishing to think that something as human as memory or thought might also be an echo of this principle. Patterns written across the brain's surface, correlations linking neurons into a geometry of awareness. Maybe our consciousness too is a kind of holographic projection, a three-dimensional feeling drawn from a two-dimensional map of connection. Whatever the case, the boundary between physics and philosophy seems to blur here. The universe no longer feels like a stage we stand upon, but like a story we're inscribed in. The walls around us don't confine. They contain everything that ever was, each vibration preserved as information, each moment etched into the fabric of reality. If we follow the thread further, there's another whisper waiting. Some physicists now suspect that these networks of entanglement, these invisible bridges, might be more literal than we think, that every bond of correlation could also be a path through space, a tunnel connecting distant points, a hidden shortcut in the fabric of reality. Imagine 2 points in space, 2 distant stars, or perhaps 2 atoms, or even 2 particles separated by light years. Between them, you might picture emptiness, a stretch of nothingness vast and silent. But physics has begun to whisper something astonishing, that emptiness may not be empty at all. Beneath the surface of space there might be threads, tiny bridges of connection that stretch invisibly between places once linked, threads woven out of the same strange fabric we call entanglement. A century ago, no one could have imagined that such invisible bonds might exist. Even Einstein, who helped give us the modern picture of space and time, called entanglement spooky action at a distance. To him, the idea that 2 particles could stay connected no matter how far apart they were seemed to defy everything he believed about locality and cause. But as experiments accumulated, one after another, the spooky part became unavoidable. The universe really does behave as though distance is optional when 2 systems share information. In 2013, 2 physicists, Juan Maldacena and Leonard Susskind, proposed a gentle but radical idea to explain this. They suggested that entanglement and the geometry of space might actually be the same thing described in 2 languages. Their shorthand for it was simple. ER equals EPR. Those 3 letters hide an entire revolution, ER refers to Einstein-Rosen bridges, the theoretical tunnels we now call wormholes. EPR refers to Einstein, Podolsky and Rosen, the same trio who described quantum entanglement back in 1935. The claim was that each pair of entangled particles could be thought of as being connected by a microscopic wormhole. The bridge isn't a tunnel you could travel through. It's a symbolic link, a gentle curve in the fabric of space-time that represents their correlation. You can imagine it like this. If the universe were a vast sheet of fabric, entanglement would be the stitching that holds distant patches together. A wormhole isn't so much a hole as it is a fold, a shortcut made possible by shared information. In this picture, space itself is born from the total web of entanglement. Where connections are strong, the fabric tightens. Where they weaken, distance grows. It's not the kind of idea that can be seen under a microscope, but it has inspired deep mathematics and even laboratory analogues. In late 2022, researchers used a small quantum computer to simulate the behaviour of such a bridge. They didn't open a tunnel through space, of course, but they demonstrated how information sent through one quantum system could emerge in another, as if it had passed through a hidden channel. The media called it a baby wormhole, but it was really a metaphor brought to life, a reminder that entanglement can make distant systems act as one. If you want to picture this in everyday terms, think of two musicians improvising on opposite sides of the planet. Without speaking, they begin to play in sync, each anticipating the other's rhythm. The harmony doesn't travel between them as a signal. It arises because they share a deeper beat, a common pattern. Entanglement is like that. Connection without communication, resonance without exchange. From this perspective, space is not a void, but an enormous woven structure, and the threads of that weave are lines of correlation. Every particle, every atom, every star is part of this web. When physicists calculate the distance between 2 points, what they're really measuring is how much information connects them. The more entangled, the closer they are in the hidden geometry. That idea redefines what it means to be somewhere. You're not just located at a position in space. You are defined by your pattern of connections to the rest of the universe. Two regions that share no entanglement are, in a sense, infinitely far apart. Those that share much are near, even if separated by cosmic miles. There's a quiet poetry in that. It means that closeness, even in the physical sense, is not about meters or miles, but about shared structure, about harmony. A person you love, though halfway around the world, can feel close, because you share a deep pattern of information, a bridge invisible but real. The same language that describes quantum systems can describe the ties between minds. When you think of wormholes, you might picture science fiction, portals, tunnels, spaceships slipping through shortcuts in space-time. The truth, though more subtle, is no less wondrous. Wormholes are symbols of unity, not escape routes. They remind us that what the universe values most is connection. In every equation describing space-time, what matters is not the objects themselves, but the relationships between them, the way their existence echoes across the web of everything else. If entanglement and geometry are truly one and the same, then perhaps space is nothing more than the sum of all possible understandings, an ever-changing network of mutual recognition. The cosmos holds itself together by remembering itself, each point keeping faith with the rest. This realization bridges more than physics. It touches something human. We often feel alone, isolated by the vast distances of space, time and circumstance. But beneath those distances lies a shared structure, a continuity that never fully breaks. Every atom in your body was once part of the same star. Every breath you take mingles with molecules that have drifted through countless lungs and leaves. On the deepest level, you are connected to everything that ever was. The universe is entangled with itself, and you are part of its conversation. Perhaps that's what these ideas have been pointing toward all along. that reality is not built from separation but from relationship. Entanglement is the grammar of existence, the rule by which the cosmos writes its sentences of matter and motion. Wormholes, then, are the punctuation, the commas that link clauses across infinity. When we look at the universe this way, even its most mysterious structures start to feel intimate. Black holes are not voids but archives. Space is not emptiness but a weave of understanding. Distance itself is only a translation of how connected things are. And in that quiet revelation lies a profound symmetry. The same principle that binds subatomic particles may also bind galaxies, minds, and moments. Everything that communicates, remembers, or resonates is part of the same pattern. The bridges made of entanglement are everywhere, holding the universe together like threads of light in an unseen tapestry. As we drift gently forward in our journey, it's time to turn toward the other great illusion, the one that seems to carry us all in its current. We've explored the fabric of space, the geometry of connection. But what about time, the soft rhythm that gives the universe its pulse, that makes change possible and memory meaningful? What if time, too, is something woven, something emergent, another song the universe sings only when we listen? Imagine pressing pause on everything. The stars, the waves, the quiet pulse of your own heart. For a moment, the entire universe stands still. Nothing moves, nothing changes. Now ask yourself, in that stillness, does time still exist? Or is time simply what we call the feeling of things changing? Physicists have asked that same question for decades. When they look deeply into the fabric of nature, especially at scales far smaller than atoms, so small that even space itself starts to flicker and lose its meaning, they find that time begins to dissolve. Below a certain threshold, sometimes called the Planck scale, the equations that describe reality no longer include an ordinary ticking clock. The math doesn't speak of before or after. It speaks only of relationships, how one part of the universe fits with another. To put it gently, the world might not have time built into it. It might create time as a kind of story. One physicist who has wrestled beautifully with this idea is Julian Barber. He argues that time is an illusion of change, that the universe in its deepest form is a collection of nows, each a complete configuration of reality. Think of them as frames on a film reel. The motion we perceive is our consciousness moving from one frame to the next, giving life to the illusion of flow. The frames themselves are timeless. It is our minds that knit them together into melody. Carlo Rovelli, another thinker who has spent his life studying the nature of time, offers a similar idea through what he calls thermal time. In his view, time isn't a universal river flowing at a fixed rate. It's a local current, born from change in temperature and complexity. Wherever things can evolve, wherever energy can spread, we experience time. But if the universe reached perfect balance, if nothing ever changed, time would quietly disappear. You don't need equations to feel this truth. Think about moments when time seemed to stretch or vanish, watching a sunset, listening to music, holding someone's hand. The seconds on the clock kept passing, but your experience detached from them. The rhythm of the heart and the rhythm of the world blended, and for a while you stepped outside the ordinary flow. Physics, in its own language, says the same. Time isn't absolute, it's relational. It's how change measures itself. At the smallest scales, those relations take over entirely. The equations that describe the quantum fabric of space-time, what physicists call the Wheeler-DeWitt equation, contain no symbol for time at all. Instead, they describe the universe as a single, self-consistent entity, a whole that already includes every possible moment. It's as if the cosmos were a photograph rather than a film, a picture of all events at once, without need for motion. We, the viewers inside that picture, experience the sequence of frames as history, the way a melody emerges when you play the notes in order. There's something deeply calming about that view. It suggests that nothing is truly lost, because every moment still exists somewhere in that grand tapestry of nows. The past isn't gone, it's simply another part of the pattern, woven into the whole. The future too is already folded there, waiting for our awareness to arrive. Time, in this sense, isn't a river we float down, it's the landscape we wander through, one hill at a time. To grasp this, imagine a library filled with countless books. Each book describes an entire world, a frozen moment, complete in its details. Reading one book doesn't erase the others, you simply move from one to the next, constructing a story in your mind. That's how the universe might be. Reality is the library, we are the readers, turning pages fast enough that it feels like motion. This view can feel abstract, even unsettling. If everything already is, what does it mean to live, to choose, to change? But even in a timeless picture, there's a rhythm of difference. The moments are not identical. They carry information, variety, contrast. Choice is the path through them, the thread that stitches the static snapshots into a living narrative. And from this timeless foundation, our experience of flow returns naturally. Time re-emerges wherever there is change to measure. The ticking of a clock, the swing of a pendulum, the orbit of the Earth, all are ways of comparing motion to motion, pattern to pattern. A second is not a fundamental particle, it's a ratio, a relationship. In a sense, every clock is a storyteller. It turns the universe's stillness into a tale of becoming. Without such storytellers, without processes that mark the difference between now and later, the cosmos would be a single note held forever. And perhaps that is what lies at its deepest layer, a stillness so complete that movement, sound and memory are born from it like ripples on water. Barber once said that if we could see reality as it is, unfiltered by our sense of duration, we'd find an infinite gallery of moments, each timeless and complete. To be alive is to walk among those moments, stringing them into continuity, feeling them as a heartbeat of before and after. If time truly emerges from change, then the sense of direction we feel, from past to future, must also arise from deeper laws. Why do we remember yesterday but not tomorrow? Why does the arrow of time point one way? That's the mystery waiting just ahead. But before we move on, it's worth pausing here, in this quiet stillness, and noticing what the idea offers. A timeless universe doesn't make life meaningless. It makes every instant sacred. Each moment, each gesture, each breath is an eternal piece of the whole, shining independently, never erased. As we drift gently onward, we'll listen for the reason the arrow points forward, why tea cools, why stars burn out, and why, even in a timeless cosmos, we still feel the pull of tomorrow. Think about the small rituals that mark the passing of your days, a cup of tea cooling beside you, the warmth of sunlight fading as the evening deepens, the way a memory feels sharper when it's new and softer as it drifts into the past. Each of these things seems to move in only one direction. The tea never grows hot again on its own. The sunlight never brightens once the sun has set. Time, in our experience, always flows forward. But nature's laws, at their deepest level, don't actually prefer forward over backward. The equations that govern how atoms move, how fields vibrate, how particles dance, all of them are symmetrical. They work just as well in reverse. So where does the one-way arrow of time come from? Why does the universe remember yesterday but not tomorrow? Why do we grow older, not younger? To find the answer, we have to look not at the tiniest details of physics, but at the grand statistical scale of things, at the way countless small interactions combine into patterns. This is where the idea of entropy comes in. Entropy is often described as disorder, but that word can sound misleading. It's more accurate to call entropy a measure of how many ways something can be arranged without changing its overall character. The higher the entropy, the more possible arrangements there are. A tidy deck of cards, perfectly ordered by suit, has low entropy. Shuffle it, and the entropy rises, because there are vastly more ways for the deck to be mixed than arranged. Now imagine the entire universe as a cosmic deck of cards. Right after the Big Bang, it was in a very special state. Exquisitely ordered, low in entropy. Over time, as matter spread out and stars formed and died, that order began to unravel. The universe has been shuffling ever since. The arrow of time is simply the direction in which entropy increases, from order to disorder, from unlikely to likely, from specific to diffuse. This might sound abstract, but you can feel it everywhere. When an ice cube melts in a glass, the structured crystal of frozen water dissolves into random motion. The molecules become free, chaotic. That's entropy increasing. The same happens when perfume spreads through a room, or when heat moves from your tea into the air. Energy flows from concentrated forms to diffuse ones, because there are more ways for it to spread than to stay contained. It's not a law of preference, it's a law of probability. The reason you can remember the past but not the future lies in this same asymmetry. The past was more ordered, a specific arrangement that left records and memories behind. The future, with its higher entropy, has more possible outcomes and therefore fewer constraints. Memory is the universe keeping track of its lower entropy configurations. You recall where you were an hour ago because those conditions have left structured traces, neurons wired, signals recorded, stories preserved. The future hasn't yet carved its traces into matter. This way of thinking about time, as a gradient of possibility, gives a new meaning to everyday experience. The steam rising from your cup, the fading of colour in an old photograph, even the gentle aging of your own hands are all expressions of the same rule. The universe is exploring its possibilities. Entropy doesn't destroy, it diversifies. It's the process by which the cosmos discovers every way it can be. And yet, within that grand drift toward disorder, small pockets of order arise. Stars form from collapsing gas. Planets emerge from cosmic dust. Life somehow appears and sustains itself for a while against the current, building structure from chaos. We are one of those small temporary miracles, islands of low entropy powered by the sun's steady flow of energy. Every heartbeat, every breath, every thought is a local reversal of the general trend, a little eddy in the larger river of increasing entropy. If you listen carefully, there's something strangely comforting in that. The arrow of time is not an enemy. It's the universe's way of growing, of exploring. The same process that melts your ice cube also fuels the birth of stars. Heat lost here becomes warmth elsewhere. Order dissolves in one corner so that complexity can rise in another. From a cosmic viewpoint, the increase of entropy is what allows time to have texture. Without it, everything would happen at once with no before or after. As physicist John Wheeler once said, time is what keeps everything from happening all at once. The arrow gives a sequence, it makes stories possible, even consciousness depends on it. The very act of thinking requires memory, a record of what just happened. Without the asymmetry of entropy, no record could form, no thought could follow another. We would exist in a blur of simultaneous moments, unable to notice ourselves. Time's arrow, drawn by entropy, is the sketch of awareness itself. There's another layer to this story, one that ties the arrow of time to the origins of the universe. For reasons no one fully understands, the cosmos began in an extraordinarily low entropy state. That's why there's a direction for entropy to increase. If the universe had started in perfect equilibrium, everything would have been evenly spread, nothing to change, nothing to notice. But it didn't. It began young, hot, and improbably ordered. the cosmic equivalent of a freshly shuffled deck stacked neatly in sequence. That improbable beginning gave time its forward lean. What we call the flow of time may simply be the universe remembering that special beginning, unfolding away from it, exploring every possible arrangement that can follow. The arrow of time points outward from that moment of improbable simplicity toward the vast landscape of complexity we see today. When you look at the night sky and see the Milky Way stretching across the darkness, you are witnessing the arrow in action, the light of ancient stars travelling forward through space and time, carrying entropy's quiet message. Everything that happens, from the drifting of clouds to the growth of trees to the thoughts forming now in your mind, is part of that same irreversible unfolding. It's easy to feel small in this picture, but perhaps we can also feel something else: gratitude. The arrow of time, drawn by entropy, gives meaning to our experiences. It allows us to remember, to learn, to change. It's why stories exist and why each moment feels precious. If time didn't flow, nothing could be lost, but nothing could be found either. In the next step of our journey, we'll take this one step further. If time has an arrow and yet the deepest equations of the universe are timeless, maybe what we call flow is not the ticking of a clock, but the execution of a pattern, a computation running quietly beneath all things, rules without a clock, a rhythm without a beat. Picture the universe long before the first clock ever ticked, before suns turned, before atoms spun, before anyone could measure before. There were no gears, no pulses, no rhythmic motion to count. Yet something existed, quietly obeying its own consistency. In that timeless stillness, the universe was already solving the equations that would one day allow clocks to exist. Physicists sometimes joke that time is what we invented to keep everything from happening all at once. But at the deepest level, nature doesn't seem to need a watch to know what to do next. Many of the equations that describe the universe, even the grand ones that include gravity and quantum mechanics, have no explicit symbol for time at all. They describe a world that simply is, not one that ticks. One of these formulations, often called the Wheeler-DeWitt equation, portrays the entire cosmos as a single, self-consistent whole, an interlocking puzzle where all events coexist in one grand pattern. If written on a board, it would look eerily still. No term for seconds, no flow from past to future. It's not that time is denied, it's that the universe doesn't need it to exist. It's a timeless arrangement of possibilities, always complete. To feel this, you don't need to see the math. Think instead of a symphony frozen on the page. Every note, every rest, every crescendo is there at once, ink on paper. When the music is performed, time comes alive. Not as something the sheet music possesses, but as something the listener experiences. Time is the act of playing. In the same way, the universe's equations contain the whole score, and we, the conscious observers, are part of the orchestra bringing it to life. There's something humbling in that view. It suggests that time is less like an external current carrying us forward, and more like a relationship between patterns. When the patterns change relative to one another, we perceive motion. When they align, we call it stillness. It's the comparison, not the clock, that gives time meaning. This becomes clearer when you think about what a clock really does. Take a simple pendulum swinging back and forth. Its motion is regular, predictable, but it doesn't create time. It marks it. The pendulum is just a pattern repeating itself. What we call a second is the ratio between that repetition and other processes we care about. A heartbeat, a spoken word, the turning of the earth. If all motion in the universe slowed down or sped up together, we'd have no way to notice. There's no absolute rhythm underneath it all. Time is relational, not universal. Even the famous theory of relativity whispers this truth. Time for you and time for me are not guaranteed to agree. A clock on a fast-moving spaceship ticks slower than one on Earth. A watch near a massive star runs more slowly than one in empty space. Gravity stretches time, motion bends it. Yet each clock believes it's keeping perfect time in its own frame. There's no single cosmic metronome clicking in the background. There are only local beats, all valid, all part of the same overarching harmony. This relativity reminds us that what we call now is a slippery thing. Your now and mine are slices through the same four-dimensional fabric, tilted differently depending on where and how we move. The universe doesn't split itself into past, present and future. We do, carving out sequences from an unbroken whole. The flow of time may be more like the movement of a flashlight beam across a painting. Each sweep reveals a part of the picture, but the entire canvas already exists. There's a quiet freedom in realizing that the universe doesn't march to a drum beat. Clocks, in the end, are conveniences, beautiful approximations of something far deeper. Beneath their ticking lies a timeless logic, rules and relationships, cause and effect woven into one consistent pattern. Time, as we experience it, may be nothing more than the way consciousness steps through that pattern, frame by frame, like a reader turning the pages of an eternal book. We can find echoes of this even within ourselves. Think about moments when you lose track of time, absorbed in music, in work, in the presence of someone you love. The usual rhythm fades and you feel suspended, weightless. Your inner clock quiets, but the world continues effortlessly. Physics offers a similar vision. The universe doesn't stop when clocks stop. It never depended on them to begin with. Some researchers have suggested that time might emerge from entanglement, the same web of connection that holds space together. When two systems interact and share information, a kind of internal ordering appears. One can serve as the clock for the other. The flow of time, then, may be a byproduct of interaction itself, a story written whenever two parts of the universe compare their states. In a completely isolated system, where nothing changes relative to anything else, there would be no time, just quiet being. You can picture this as dancers on a stage. The music starts only when at least two move in relation to each other. If everyone froze, the rhythm would vanish, though the dancers would still exist. Time is the dance, not the stage. This understanding leads to a subtle but beautiful idea. If time isn't fundamental, then the laws of physics might be more like the rules of a computation, a vast ongoing process that doesn't require a metronome. The universe could be running its own logic, exploring every possible configuration of fields and matter, not step by step, but all at once. What we experience as the passage of time could be our limited way of reading that computation, one frame at a time. In that light, our existence becomes even more remarkable. We are part of the universe, learning to feel its own rhythm, inventing clocks to count what it already knows without counting. Every second that passes is a tiny act of translation, the timeless cosmos speaking through the language of change. When you hold a watch and see its hands move, remember that you're watching patterns comparing themselves. The watch doesn't measure time, it creates it, moment by moment, as it interacts with your awareness. The tick isn't the universe's heartbeat, it's ours. And so, time, once thought to be the ruler of all things, becomes something gentler. A story we tell about relationships, a melody played by motion and mind. The deeper truth is timelessness, the silent structure beneath the ticking, the stillness that allows every rhythm to unfold. From here, as our journey continues, we'll look beneath even that stillness. If time and space can both emerge from information and relationship, perhaps the universe itself is a kind of code, a computation endlessly running, not in seconds or years, but in meaning, a cosmos without a clock, yet full of order, a pattern unfolding because it can. Imagine holding a simple switch between your fingers, the kind that can be either on or off, light or dark, yes or no. On its own, it feels meaningless. But when you string enough of those switches together, they can draw a picture, play a song, or tell a story. Every video you've ever watched, every message you've ever read, every photograph you've ever saved, all of it, at the deepest level, is made of tiny decisions, ones and zeros, yes and no, light and dark. Now imagine that the universe might be built the same way. Not from matter, but from choices. Not from things, but from answers. That was the radical idea proposed by the physicist John Archibald Wheeler, one of Einstein's last students, a man who spent his life pondering how the universe keeps its own records. Wheeler looked at all the strange revelations of modern physics, quantum mechanics, relativity, information theory, and wondered if they were pointing toward a single truth, that reality itself might be built from information. He called this idea it from bit. In his words, every it, every particle, every field, every patch of space-time derives its existence from binary choices, from yes or no questions, from bits. The universe, he suggested, isn't a static collection of things, but an ongoing process of inquiry. It doesn't merely exist, it answers. You can feel the elegance of that idea without touching any mathematics. Think of a question as a small disturbance in the void. Is there light here? Is the particle spin up or down? Did the photon go left or right? Each question, when answered, gives birth to an it, a piece of the physical world. Every measurement, every act of distinction, adds one more bit to the cosmic conversation. Our digital world provides a perfect metaphor. A photograph of a sunset looks rich and continuous, but under a microscope it's only pixels, each one storing a binary choice of light or dark, red or not red. Enough pixels together create the illusion of smoothness. Likewise, DNA stores the instructions for life using 4 chemical letters. But all of biology's diversity emerges from simple yes-no pairings along that molecular script. Wheeler's insight was to take that logic seriously on a universal scale. If the smallest units of matter and energy are fundamentally unpredictable until measured, as quantum mechanics tells us, then perhaps the act of measurement is the act of creation itself. The universe, in this view, isn't a giant machine running on gears. It's more like an ever-growing database, each observation adding another entry. When you turn on a light and the room brightens, you've just added information to the universe. The lamp is on. When a photon from a distant star strikes your eye, you've completed a process that began billions of years ago, finalizing one more answer in the cosmic ledger. Even silence contributes. Every unobserved possibility remains suspended as potential, until some question, human or otherwise, collapses it into a fact. Of course, this doesn't mean that reality depends on us personally to exist. Wheeler didn't claim the universe needed humans to look at it. He suggested that it's inherently participatory. Every interaction, from particle to planet, is a kind of measurement. The cosmos asks and answers itself continuously. Electrons scattering off atoms, stars curving light through gravity, galaxies tugging on each other through the deep fabric of space. Each interaction is another bit written into the grand archive, and just as there's a limit to how many pixels can fit on your screen before the image blurs, the universe too seems to have a maximum information capacity. Physicist Jacob Bekenstein discovered that any region of space can only hold a finite amount of information, proportional not to its volume, but to its surface area. In simpler terms, there's only so much detail reality allows in any patch of space, like a photograph that can store only so many pixels per inch before it turns to haze. The cosmos, though vast, still follows a rulebook of information density. This limit connects beautifully to what we've already explored, the holographic principle, where everything inside a region can be described by what's written on its boundary. Taken together, these ideas suggest that existence itself may be a vast self-consistent data structure. Matter, energy, gravity, and even space-time could be the macroscopic shadows of information relationships, woven together in patterns so intricate that they appear continuous. It's tempting to imagine the universe as a colossal computer running this code, but that image can mislead. Computers process data according to human time, step by step, tick by tick. The cosmos, however, has no clock outside itself. Its computation isn't something happening in time, it's what creates time. Instead of a machine, it may be closer to a question forever unfolding its own answer, a story that keeps writing itself to see where it will go. If you look around right now, the light reflecting off the walls, the sound of your breath, the warmth in the air, you're surrounded by the results of countless cosmic bits already resolved. But at the same time, innumerable others hover in possibility, waiting to be asked. The fabric of reality is less a finished tapestry than a conversation still underway. This idea doesn't reduce the world to cold logic, it gives it new intimacy. Because if everything is information, then interaction itself becomes sacred. Every exchange of words, of energy, of touch is a small act of participation in the universe's ongoing dialogue. Even uncertainty begins to feel beautiful here. The gaps between answers aren't mistakes. They're the spaces where new questions can form. Without them, the story would end. Perhaps what we call existence is simply the universe forever asking itself, what happens next? Wheeler once drew a small sketch to illustrate his idea. A big letter U, representing the universe, with a tiny eye drawn on one end, looking back at itself. That, he said, is the participatory cosmos, an infinite system that through consciousness has learned to notice its own existence. If the universe truly runs on bits, on yes or no questions, on acts of distinction, then it isn't just a machine executing commands. It's a conversation, alive and recursive, where each answer invites a new question. The world is not merely being, it's forever becoming. And as we drift further into this thought, we begin to wonder, if the universe is a vast informational sea, what kind of patterns might emerge when simple rules interact again and again? Could meaning itself be the result of computation? Simple laws weaving infinite beauty, like snowflakes from air? Close your eyes for a moment and imagine that the universe could be paused, like a frame in a film. If you could zoom into that frozen picture, deeper and deeper, perhaps you'd see not particles or waves, but patterns, lines, connections and relationships. Not a machine of metal and motion, but a network of logic, as if existence itself were written in code. That is the idea some scientists have begun to take seriously, that the universe may not merely be described by mathematics, but may be mathematics. Its essence could be rules, simple, elegant, and endlessly generative, that produce everything from galaxies to thoughts. Physicist Stephen Wolfram has spent decades exploring that possibility through what he calls cellular automata, tiny worlds governed by simple rules. In his models, a line of pixels begins blank. You tell it, if a pixel's neighbours follow a certain pattern, light up. If not, stay dark. That's it. One line of instructions. Then you press play. What emerges is astonishing. From such simplicity, bloom shapes that look like coral reefs, lightning bolts, even organisms that move and replicate. Patterns that seem random but are perfectly deterministic. Chaos from clarity. You don't have to understand the mathematics to feel the poetry of it. Imagine a field of snowflakes falling, each one built from the same rule of freezing water, yet no two alike. Or think of the game of life, a computer simulation invented by John Conway in the 1970s. On a grid of squares, each cell lives or dies according to how many neighbours it has. The rules fit on a napkin, but when you let them run, entire ecosystems appear. Shapes that crawl, split, reproduce and vanish. It's mesmerising to watch order and unpredictability dance hand in hand. Wolfram believes the same principle might underlie reality itself, that the universe is a kind of vast automaton, following simple local rules at every point in space. Each update of those rules gives rise to what we experience as the next moment. We don't see the rules directly, we see the ripples of their consequences. If this is true, then the richness of the world, light, colour, gravity, emotion, may be the visible face of a code running beneath everything. And that code may not be complicated. It could be as simple as a handful of mathematical relationships repeating themselves everywhere, creating a grand pattern too vast to see all at once. Max Tegmark, another physicist, takes this one step further with what he calls the mathematical universe hypothesis. He suggests that the universe doesn't just use math, it is math. Every structure that can exist mathematically exists physically somewhere, as part of a grand ensemble of realities. In other words, existence and mathematical consistency might be the same thing. Wherever logic can hold, reality follows. It sounds abstract, but think of it this way. A circle drawn on paper and a wheel rolling down a road both obey the same geometry. The wheel's motion is simply geometry given weight. Tegmark's idea suggests that our universe is geometry and logic given existence, that being is the natural expression of mathematical truth. The idea may feel unsettling, but it carries a quiet beauty. It means that the universe's complexity doesn't depend on a grand plan. It can arise naturally from simplicity. A few fundamental rules, written in the language of relationships, can unfold into stars, seas, and sentient minds. Determinism and wonder coexist, like two sides of the same pattern. To make this more tangible, think about music. Each note follows a rule, frequencies doubling or halving, rhythms dividing time. Yet from those rules comes emotion, depth, surprise. The same could be said of mathematics. The rules of numbers are fixed, but their combinations give rise to infinite melodies of possibility. Perhaps reality itself is the music played by mathematics, and consciousness is the act of listening. And even in a universe built on rules, unpredictability remains. Many systems, including the ones Wolfram studies, are deterministic but uncomputable. That means the only way to know what they'll do next is to let them evolve and watch. The rules may be simple, but their outcomes can never be fully predicted. Even the cosmic code contains mystery. This paradox, order giving rise to spontaneity, feels strangely human. We too are beings of pattern, following rules of biology and chemistry, yet capable of creativity, love, and imagination. Within the deterministic framework of physics, something unpredictable blooms, meaning. The same principle that governs the dance of galaxies allows for poetry, laughter, and awe. When you look at a tree, you can see this logic in its branches. Each split follows a rule: divide, grow, repeat. Yet no two trees are identical. The rule gives form, but the world gives context. And somewhere between rule and randomness, life finds its rhythm. The deeper scientists look, the more the universe appears to run on such patterns. Self-organizing, recursive, elegant. Each particle moves not because someone pushes it, but because it is following the simplest possible rule that remains consistent with everything else. The result is not chaos, but harmony. An enormous evolving equation that writes and rewrites itself with every moment of being. It might sound cold to imagine the universe as a computation, but perhaps it's the opposite. If reality is code, then it's the most beautiful kind, one that contains its own interpreter, one that dreams, asks, and wonders about itself. We're not separate from that code. We are the part of it that reads. You can even think of your own mind that way. Every thought you have is an arrangement of information, a pattern flickering in the brain's electric field. But within those patterns, something emerges that isn't reducible to bits. The feeling of being alive, the sense of self. Just as the game of life can spawn patterns that move as if they have agency, the universe may have given rise to beings capable of noticing the game itself. And that brings us to a profound question. If the cosmos truly is a grand computation, who or what observes it? Does it need an outside witness, or does it compute itself into awareness? When the universe runs its own code, who is reading it? In the next step of our journey, we'll turn inward to that very mystery, to the strange possibility that awareness, far from being an afterthought, might be what allows the code to mean anything at all. Imagine waking up before sunrise. The world outside is still quiet, just a faint hum of possibility. Then, as light seeps through the window, the room begins to take shape. The edges of objects return, the air shifts, and suddenly you are there, aware. The scene hasn't changed much since you were asleep. What changed is that now the universe has begun reading itself through you. This is where our journey through information becomes personal. For all the talk of fields, waves, and algorithms, something remarkable happens at this particular scale of reality. The code begins to feel. Out of patterns of information, awareness emerges, not as an accident, but as another form of structure. To describe this, some scientists turn to a theory known as Integrated Information Theory, or IIT. But we can forget the name and hold the essence. Consciousness may arise when information becomes deeply interconnected, when every part of a system influences and is influenced by the whole. In other words, when information doesn't just exist, it begins to feel its own pattern. Picture a single drop of water falling into a still pond. The ripples spread outward, touching every point on the surface. Now imagine countless drops falling at once, their ripples crossing and merging until the surface becomes one complex, self-interacting wave. According to this view, consciousness might be something like that, a state of information so tightly integrated that the ripples can no longer be separated from one another. The whole system, in some quiet sense, knows itself. In the human brain, this manifests as countless neurons exchanging signals, electrical, chemical, rhythmic. Each cell, by itself, is simple, but together, in their billions of connections, they create a pattern so rich that it generates awareness. The brain doesn't merely process information, it integrates it into a single, unified experience, the feeling of you. What makes this idea powerful is that it treats consciousness not as a ghost or a miracle, but as an intrinsic property of certain kinds of organization. It doesn't require a divine spark or a special material. It only requires enough complexity, enough interdependence, enough feedback for a system to light up from within. Even the universe, seen this way, could be viewed as the largest integrated network of all, a grand, self-referential field of awareness diffused across its structure. This leads naturally to another idea, one that takes the participatory universe from Wheeler's it from bit and turns it gently toward the subjective, cubism, or quantum Bayesianism. In this interpretation, quantum theory isn't a cold description of external objects. It's a language of belief, describing how observers update their expectations when they interact with the world. In other words, reality is not a fixed stage waiting to be seen. It is a web of relationships where each observer's act of noticing reshapes the pattern of probabilities. When you measure something, you aren't revealing a pre-existing fact, you're participating in the making of it. Every observation is personal, unique to the observer's history and perspective. Yet collectively, they all weave together into the shared fabric of what we call reality. You can feel the beauty of this idea without equations. Imagine billions of mirrors scattered across a hillside, each angled slightly differently, each reflecting the same sun in its own way. From afar, they sparkle as one dazzling surface. Up close, each holds its own piece of light. That is Cubism's universe, a cosmos that exists through reflection, where every conscious being offers a different view of the same truth. Both of these ideas, integrated information and participatory observation point toward a single, gentle possibility: that awareness is not a late arrival in the universe, but an inseparable part of its design. The cosmos may not just be computing, it may also be perceiving the computation as it happens. Consciousness and reality could be two sides of the same mirror, each giving the other meaning. When you sit quietly and watch your own thoughts come and go, when a memory rises or a sound reaches your ear, what you're witnessing may be a miniature version of that cosmic dialogue. The brain asks, the world answers, and in between those two movements arises the soft glow of experience. You, in that moment, are the meeting point between information and awareness. It's tempting to think that consciousness is rare, a fragile flame flickering on a tiny planet. But perhaps it's more accurate to say that consciousness is what happens whenever the universe becomes complex enough to notice itself. Every nervous system, every flicker of perception, is a small aperture through which the cosmos peers back. We are not outside the grand computation. We are part of it, the part that asks, what does it mean? And that question, what does it mean, is the bridge from physics to philosophy, from syntax to semantics. Physics describes the structure of information, the syntax of reality, how things relate, how energy transforms, how matter behaves. But syntax alone doesn't carry meaning. A poem written in an unknown language is still beautiful, but it doesn't speak until it's understood. Meaning is what happens when awareness reads the syntax. You can imagine it like sheet music. The notes on the page are the syntax, perfectly structured, mathematically precise, but the melody, the emotion, the life, that's semantics. That's what arises when someone plays it, when the notes become sound and the sound becomes feeling. The universe, too, may have its sheet music written in equations and relationships. Consciousness is the musician that brings it to life. In this light, perhaps physics and mind are not separate realms, but complementary halves of a single system. The universe provides the grammar, and consciousness provides the interpretation. Each gives the other existence. Without structure, there could be no experience. Without awareness, the structure would have no meaning. This union between matter and meaning, between code and comprehension, might be the deepest truth we can glimpse. It suggests that reality is not just a story being told, but a story being heard. The listener and the speaker are the same. And when that realization settles, quietly, a new question begins to form. If syntax and semantics meet in us, where did either of them begin? If meaning arises from awareness, and awareness arises from the universe, what lies beneath them both? What was there before the first word was spoken, before the first yes or no was chosen, before even the idea of existence appeared? The next part of our journey turns toward that final mystery, the stillness beneath structure, the silence beneath sound, the nothingness that isn't empty at all. If you've ever watched a musician sit quietly before a piano, you'll know there's a strange beauty in silence. The keys wait, perfectly ordered, perfectly capable of producing harmony, and yet nothing happens until the first note is touched. The potential for music is there, the syntax, but the melody, the meaning, is still asleep. Physics, in many ways, is like that piano. It gives us the grammar of the universe, the rules of combination, the logic of cause and effect, the relationships between things. It tells us how particles interact, how gravity bends light, how energy transforms, but it does not tell us what any of it means. The laws are syntax, consistent, exquisite, universal, but they are not the story itself. Meaning, it seems, arises only when something reads the grammar. When awareness, however you define it, interprets the structure and turns pattern into purpose. The same equation that describes the orbit of a planet can also describe the path of an electron, but it takes a mind to see beauty in the symmetry. Without the reader, the story remains ink on a page. You can sense this distinction everywhere in daily life. A page of sheet music means nothing to a cat, but everything to a pianist. A book written in an unknown language is still a book, its syntax intact. Yet it holds no story until someone who understands the language opens it. The same can be said of the universe. Its syntax, the physical laws, existed long before us. But meaning only appears when there is something capable of noticing, reflecting, and asking questions. This doesn't mean that reality depends on humans to exist. The stars would burn with or without our eyes to see them, but the act of seeing transforms what existence feels like. It turns radiation into beauty, vibration into song. Awareness completes the circuit between structure and significance. You can think of the cosmos as a vast book written in equations. The grammar of that book, energy, momentum, geometry, is perfect, but utterly impersonal. It tells us how things happen, never why. That tiny word, why, belongs to meaning, and meaning requires readers. Perhaps that's why consciousness arose, not as an accident, but as the universe's way of reading itself aloud. In this sense, we are not outside observers peering into a cold, mechanical world. We are participatory interpreters of its syntax, translators of its logic into feeling. The blue of the sky, the warmth of the sun, the ache of longing, all are expressions of structure transformed by awareness. The laws of physics didn't create love, but they created a universe where love could arise, where the syntax of matter could be translated into emotion. The mathematician Eugene Wigner once wrote about the unreasonable effectiveness of mathematics, the uncanny way that abstract numbers seem to describe the physical world so precisely. He called it a mystery, verging on a miracle. Why should the universe be written in such perfect grammar? Why should equations, invented in the human mind, fit the stars? Perhaps the answer lies in the fact that we and the stars share the same syntax. Our minds are built from the same laws that govern the cosmos. The grammar of the universe is the grammar of thought itself. When we do mathematics, we're not imposing order on the world. We're uncovering the order we already belong to. And yet, that order still feels incomplete without meaning. Syntax can explain why a rainbow curves, how light refracts, even predict its exact angles. But only meaning can explain why it moves us, why a simple band of colour can make us pause, smile, and feel wonder. That bridge from knowledge to awe is something physics cannot cross on its own. It requires the subjective, the interpretive, the poetic. You might say that physics writes the notes, and consciousness plays the melody. Without the player, the notes stay silent. Without the notes, the player has nothing to express. It's a partnership. Syntax and semantics, rule and resonance. One defines possibility, the other brings it to life. This partnership raises a haunting question. What was the universe before readers existed? Before eyes, before minds, before the first creature ever looked up at the stars, did meaning exist at all? Was the cosmos a beautiful but silent manuscript, waiting through endless time for someone to open it? Or was meaning already there, not as thought, but as potential, like the promise of music before a single note is played? Perhaps meaning doesn't require an audience in the usual sense. Perhaps the act of existing is already a form of expression. Every atom, every photon, every curve of space-time could be the universe declaring, "I am." In that light, awareness isn't the start of meaning, it's one of its later verses, the universe finally learning to understand the poem it's been writing since the beginning. You can sense this unity in small things. When you hear the wind move through leaves, there's a structure, a pattern of pressure waves, a precise dance of molecules. Physics can describe every vibration. But what you feel, the hush, the whisper, the serenity, is meaning. It's the syntax of nature turned into the semantics of experience. And maybe this is what it means for us to exist. to act as translators between the grammar of the universe and the language of the heart. We take equations and turn them into stories, stars and turn them into constellations, noise and turn it into music. Without us, the universe would still be perfect, but it might be lonely in its perfection, unseen, unread, unplayed. So the next time you look at a night sky scattered with stars, imagine it as a vast sentence written across darkness, grammar without interpretation. And then remember that by noticing it, by feeling awe, you've added the missing punctuation. You've turned syntax into story. If we follow this trail of thought a little further, it leads to a final, quiet place. If meaning arises when the universe reads itself, what lies beneath both meaning and structure? What is the silence from which both the grammar and the music emerge? The nothingness that still somehow trembles with potential? That is where our journey will end, in the calm and curious heart of the void. Before there was light, there was stillness. No stars, no sound, no space to hold them, only an unbroken quiet. Too complete for even silence to describe. But even that perfect stillness wasn't truly empty. Beneath it lay a kind of tension, a poised readiness, as if the universe were holding its breath, waiting for something to begin. When we talk about nothing, our minds tend to picture a blank void, a black screen without colour or sound. But physics has slowly revealed that this image of nothingness is only an illusion of simplicity. The vacuum, the closest thing we can reach to absolute nothing, is in truth a restless sea. Even when stripped of all particles and light, space still trembles with invisible energy, humming at the faintest possible level. This is what physicists call the quantum vacuum, though the name feels too modest for something so alive. Imagine the surface of a perfectly still pond. It looks calm, almost frozen, but beneath the glassy reflection, the molecules of water are vibrating, jittering, exchanging energy in microscopic waves. The vacuum behaves much the same way. It's not a flat nothing, but a shimmering field of potential, a quiet background where energy constantly flickers in and out of being. We can't see these fluctuations directly, but their fingerprints are everywhere. The Casimir effect, where two tiny metal plates attract each other, even in a perfect vacuum, is one of those whispers, the gentle pressure of all the unseen vibrations between them. Even the light emitted by atoms and the faint glow left over from the beginning of the universe owe part of their existence to the vacuum's eternal restlessness. In the mathematics of quantum theory, this churning sea of nothing is never truly at zero. There's always a trace, a residue of energy that can't be removed. It's called the zero-point field, the faint hum that remains even when everything else has been cooled to absolute stillness. But you don't need the equations to feel it. Just imagine the universe breathing softly beneath what we call empty space, like a sleeping giant stirring in its dreams. This realization changes the meaning of creation itself. If the vacuum is already alive with possibility, then perhaps the birth of the universe wasn't the moment something came from nothing, but the moment potential became form. A balance too perfect to last found a reason to tip, and that fall, that slight imbalance, was the beginning of everything. Physicists describe this in their own language. They say that symmetry, when it becomes unstable, breaks, and the breaking releases energy. You can think of it like a spinning coin. When it's perfectly balanced, it has no preference for heads or tails. But when it wobbles and falls, one side becomes real. The universe might have begun in just such a fall, a perfect symmetry collapsing into difference, giving rise to matter, time, and the arrow of change. Even cosmic inflation, that brief, furious expansion that followed the Big Bang, may have been driven by the energy of this almost nothing. This vacuum tension suddenly freed. Space itself stretched as if exhaling for the first time. smoothing the chaos into the vast calm we now call the cosmos. Every star, every atom, every thought we've ever had traces back to that first unevenness, the tiniest fluctuation in an ocean of stillness. If that feels poetic, that's because the truth is almost impossible to express without poetry. The universe is a masterpiece of paradoxes: emptiness that creates fullness, stillness that gives birth to motion, silence that sings. Nothingness, it seems, is not the absence of being but the raw material of it, a field of infinite potential, forever trying to express itself. Even now the vacuum hasn't stopped creating. Particle pairs still flicker into existence everywhere. Small flashes of energy borrowing time from the void, appearing and vanishing before they can be caught. They are like thoughts passing through the mind of the universe, brief but essential. The total energy of the cosmos, astonishingly, may balance to zero. Positive energy from matter perfectly offset by the negative energy of gravity. If that's true, then the universe didn't need anything to begin. It's been self-sufficient from the start, a grand equation that sums to balance. But equations are only half the story. The other half is what it feels like to live inside them. You and I are patterns rising from that same vacuum sea, brief eddies in the flow of information and energy. We are the nothingness remembering itself as form, the stillness learning to move, to think, to wonder. And someday, the motion will subside again. The universe may cool and flatten, returning to its quiet origin. Yet even then, it won't be gone. The potential will remain unspent and waiting. The story never truly ends. It only pauses between verses. When you look up at the night sky, what you see is not just stars scattered across darkness. You're seeing the echoes of that first awakening, light frozen in motion, the afterglow of nothing realizing it could be something. The space between the stars, the so-called emptiness, is the same restless vacuum that first breathed them into being. Every photon crossing that void is a reminder that creation is still happening right now in every point of space. Philosophers once said that nothingness is terrifying, the abyss we fear to face. But physics has shown that nothingness is creative. It's the background hum that makes existence possible. The void isn't a grave, it's a womb. And maybe in our quietest moments, we feel that truth intuitively. When you close your eyes and listen to the silence behind all sound, there's a strange comfort there. A feeling that the stillness isn't empty but full of presence. A presence so vast and subtle, it can only be felt, not named. Perhaps that's what we really mean when we speak of peace, the brief alignment between our small human quiet and the great cosmic quiet that underlies it. For a moment the patterns pause, the ripples still, and we sense the timeless background of all being, the same stillness from which the universe once awoke and to which it will one day return. Reality then may not be a thing that exists, but an action that continues, a performance, a behaviour, a rhythm of creation and return. Existence is the universe doing what it does best, turning potential into experience, question into answer, silence into song. And we, small as we are, get to be part of that song, tiny harmonies in a cosmic symphony still unfolding. So, as we reach the end of this journey, maybe the deepest lesson isn't about particles or time or even the birth of stars, but about perspective. To exist at all in any form is to be an expression of that infinite stillness, a wave that briefly rises and falls but never truly leaves the ocean. And as you drift into sleep tonight, remember, you're made of the same nothing that dreamed itself into everything. The silence between your thoughts is not empty. It's the quiet hum of the universe, thinking itself into being again and again.